Welcome to the Thermal Energy Network webinar hosted by NYSERDA and the Empire Building Challenge team. If you don't know about Empire Building Challenge, it was a program announced, I guess almost a year plus ago by the governor. It's a public-private partnership with leading commercial and multifamily real estate owners focused on recruiting best-in-class equipment manufacturers, solution providers, and other businesses to invest in low carbon retrofit technology development here in New York State. And these partnerships will hopefully overcome many of the barriers preventing our existing high-rise buildings from achieving aggressive energy performance and greenhouse gas emissions targets reductions, and then hopefully allowing some of these buildings to achieve carbon neutrality. If you don't know about Empire Building Challenge, or you haven't heard about some of the amazing work happening, definitely go to the NYSERDA website, get to the Empire Building Challenge page, and learn more about that, and learn more about the partners, the real estate partners that have joined this challenge. There's 10 of them. They went through a grueling process of selection. They're committing to carbon neutrality on some of their most high-profile buildings. Really hats off to them for stepping up to the plate and joining this program. So without further ado, I want to turn it over to the Gray Edge Group. Gray Edge Group specializes in architecture, engineering, and design of complex thermal energy systems using their patented thermal highway process. Successful systems are operating around the world, delivering clean and comfortable heating and cooling on projects ranging from single-family homes to large district geothermal systems, including a 123-story skyscraper. The Gray Edge Group, with 8 specialty members, they bring together unparalleled expertise with over 250 combined years of experience in all facets of the energy industry. So I will turn it over to Carrie Smith and Garen Eubank to kick this off.
All right, well, Carrie's muted, so I'll go ahead and get started. We are glad to have everybody here. We trust the information that we're going to give out is useful. And as we go through this, you'll see kind of the process that we go through to harvest, move, and reuse energy. We're finding that our loss in heat to a lower grade probably is one of our bigger opportunities to do some real savings. And so with that, Carrie, could you go to the next slide? Okay, I'm Garen Eubank. I'm the guy on the right. I'm an industrial engineer, member of ASHRAE, AEE, holding numerous certifications. I'm a fellow with them, a lot of other organizations. And so with that being said, heat transfer and the ground is kind of my area. And Carrie, do you want to explain who you are?
Yes, this is good morning, Carrie Smith, and I'm the one of the managing members of the Gray Edge and the U.S. Operations Manager. My background has been energy since 1972, and started in oil and gas to high temperature geothermal to low temperature geothermal. Our specialty is these district loops and distributed energy systems. So go ahead, Garen, and we're going to let Jared talk a little bit about the next slide, but you might want to introduce the slide.
Yeah, you'll put it up and I'll introduce it, okay? So what we're going to talk about is some of these moves and changes that we're going to see in our society. And the big overview, or the complex part of this whole thing, is first load reductions, and that can happen either from the built environment, what we do to the buildings, structures, or the equipment that we put in there and run. Secondly, we need to look at the primary energy source shifts. So we're going to be moving away from fossil fuels to other things. And like solar, which is renewable, so is ground source heating and cooling. But in truth, this whole process is not about ground source. It's about a convective circulation circuit that has many different names: 5G, 6G, 7G, 5G, DC. We've got way too many names, and we're going to try to simplify some of that for everybody. And we just call it collectively a thermal highway. And the last thing we're going to look at is the time reduction in fossil fuel use at all these facilities. There's a number of ways with plug and play components that we can get to there. And so we're starting with beneficial electrification. And Jared, do you want to take it from there, please?
Yeah, sure. There's a lot of terms flying around that we hear about. EBC, Empire Building Challenge, GEBS, grid efficient buildings, grid interactive buildings. And then there's a whole universe of terms for thermal energy networks, and also even for electrification. And so we've actually been scratching our head inside EBC around a definition for like smart electrification, so that you're not going to a 1.0 COP during the coldest times of year and blowing up the electric grid, which is a major concern. We found that there's not really a definition for smart electrification. We've been sort of living in this world or this narrative, which is a California narrative around electrification, which holds up the air source heat pump as sort of like the golden child. And yes, in a lot of ways, it's a great piece of technology, but we think in cold climates, particularly in the Northeast, we need to be a little bit smarter at how we pursue large-scale electrification of very large buildings. And just to add it to the mix, here's another term that I think we'd like to present to everyone. It's called tactical resource efficient electrification, or TREE. The TREE method of building electrification uses strategic capital planning, an integrated design process, and an incrementalistic, network-oriented approach to deliver building heating and cooling, which requires little or no combustion, enables carbon neutrality, is highly efficient at low design temperatures and during extreme weather, is highly resilient and energy grid interactive, and reduces thermal waste by capturing as many on-site or nearby thermal flows as possible. I can hand it back over to Garen or Carrie to do that next definition, which is one I think that they've been using, or we could just jump to the next slide and get into the weeds on this.
Well, we're going to talk about the Sears. We're going to talk about being practical, and we're going to use electricity and other assets that lets us multiply their outputs, which results in systems coefficients greater than 1 and coefficients of the systems greater than that of the installed box for the heating and cooling. When we network these assets, things really start coming together in a way that is beneficial to everybody. And that's kind of where that beneficial electrification comes from. But I like the term tactical, or the TREE method, because it takes us down this complex systems architecture approach, which we use at Gray Edge. That's an overview on how we're going to meet these things. Remember, I said we had 3 things earlier: load reductions, primary energy source shifts, and time reduction of fossil fuels. So with that, it lets us begin the process of capturing and reusing, the wasted heat. And we all know that we waste a lot of energy and heat in our built environment. Next slide, Carrie. What is it? Energy is recovered, reused in the process of heating and cooling buildings that the user would normally discard. Well, you can see on the left there are some outside air conditioners, and they're throwing the heat from the building outside. I don't know what that white in the foreground is, Carrie. It may be a little bit of snow. So those may be heat pumps, actually. All right. But the use of the air as the source of the sink. Next is the fire. Okay, we've got away from that. We're not living in caves anymore, so we can move on. And finally, we're getting into what most of you are going to see is some cooling towers that are using a water system to evaporate to give us a temperature change in the circulating fluid. So we want to avoid energy consumption as much as we can. How do we do that? We got to have extremely high system integrated coefficients of performance, and we define that in terms of kW, not in terms of BTU. The world uses kW, so I think we all ought to do that. The negawatt, what is that? Well, let's look at a heat pump with a coefficient of performance, or the output in BTUs divided by the input in BTUs, or the output in kW divided by the input in kW of 4. So we get 1/4, 1 out of 4 that we're going to use from hopefully a very green grid in the future. And we get 4 from the ground, or combined with the wasted energy we're going to recover. Next slide, Carrie. Now we're going to start to try to think about the magnitude to quantify this contribution or this wasted energy recovery. System coefficient of performance is the most valid way to compare competing systems. and that's the energy moved by the system to the energy input to the system. Next, the wasted energy recovery is added to the system with a very small amount of pump energy. That's pretty important to understand. Next slide, Gary. So here we're going to look at a building on the upper left that has some simultaneous heating and cooling going on. All right. So we might have some perimeter heating, core cooling, whatever. And its internal loop is satisfied. The heat pumps just are living in their own range with their own internal temperatures. And we don't need anything else from the world. And as long as it stays between 55 and 85 degrees Fahrenheit, it'll just keep chugging along. However, next, when we start getting other buildings on these systems, some may be heating, some may be cooling, depending on what they're due, we might move to what we call stage 2. So that building on the upper left, it now turns on to that central loop. If you'll look at that, that is just a big pipe, and it has a one pipe connection from the building to that central loop. Now, as long as we stay in that 50 to 85 degree range, that's all we need to do. You crank these buildings on, here it goes. However, let's go to the next slide, next click. If we have some excess, we might call for some sort of heat storage in the form of ground heat exchangers, wasted water energy recovery, solar PVT, thermal, a lot of things that we're going to start bringing in there. And those would be some of the operating plug and play component to store heat. Next, Carrie. We go to the last stage 4. In the built environment, we have cooling towers and boilers that we don't have to use all the time. If we look at temperature bands, there's a lot of times we do not need those running. And so when we get our loop temperatures a little bit further out of range, we'll simply bring in those devices to again modify that loop temperature. And so that reuses a lot of the equipment that you may have out there with no additional cost. Next slide, Carrie. So what can you do with ground source and wasted energy recovery? Well, we can increase the system efficiency considerably. 600% is pretty good, by the way. We can heat and cool air. We can heat and cool water. Okay, next. We can move energy from one building to another. This diversity that we're talking about of moving energy or heat from one building to another becomes the key to these designs, particularly on complex systems, all right? So now we're going to use the ground for simply thermal storage. And there are some areas that do some heating up a ground heat exchanger. And that's it. And it's in Alberta, Canada. Next. So we're going to level the energy loads on the system. And remember, I talked about load reductions and leveling them. Yeah, that's what we're going to do. We're going to shift the electrical demands and lower the usages. And we may be able to do that. In fact, we are. We can shed this excess energy at a time of the day that is most advantaged and recall it at the most advantaged time. And so we're going to store this energy to sell or however we want to give to others. That's up to powers beyond my control. But there has to be a way that we can share this energy in an energy commons. And in energy commons, the big problem always is who's using more than they're allocated. Well, there's ways to handle that. We're not going to talk about in this presentation, but we'll get there. Next slide, Carrie. So this is just a little diagram that I've put together. If you look at the left axis, you'll see the first line there at 1 megawatt. Go up, Carrie. There, that line right there. And so with conventional systems, all right, that have a total of 1 megawatt output capacity, how are we going to do that? Well, air source heat pumps, the problem with them is when it gets really hot or really cold, they lose capacity and efficiency big time. Ground source heat exchangers, depending on how we size that ground heat exchanger, they can get pretty efficient, but we're looking on the axis horizontally showing COP increases. And if we just simply follow that, you'll see that it would really be hard to come up with super efficient boxes or heat and air conditioning systems that really have a high COP, because you don't get much benefit once we get past about 9 or 11 on the COP. And we're finding that these thermal highways are getting into those ranges. So on this one, we've gone out and we bring back, store, recover, and reuse about 40% of the heat that is running through the system, which normally would be wasted. And we can raise that output line up. And when we do that, our COPs start going up majorly for the system, not for the box, but for the system. And so now we start approaching, instead of that 1 megawatt, 1.4 megawatt of output. Next slide, Carrie. So what we do is harvest, store, and reuse wasted energy, which is the heart of these things. To understand how this works particularly, we're going to talk about part load analysis, which is the core of these designs. At peak, all things don't operate at peak at the same time. If you've got one building, it does operate at peak, but a system does not. So let's look at this. On the left, we'll see that 50% of the peak load serves 90% of the annual operating hours. Now, in Europe, they have a similar deal called the Blauer-Engel rule, and this is basically on a pumping system for water distribution inside of a building for district systems. And we can see very similar that 50% is about, in their case, all right, is about, what is that, 79%? Well, what that's telling us is we really need to look at these part load analysis, and then we need to look at the annual hours of operation. Next slide, Carrie. So when we do that, let's look at LaGuardia. And here we have, of the 8,760 hours of operation, we have almost 7,000 hours in a range that's probably going to fit into that 50% profile. Now we have 1,000 hours for heating and have 778 for cooling, but those times at those peaks are not going to happen in each building at the same time, which now says, yes, the building is going to hit its peak, but not all the buildings are going to hit their peaks at exactly the same time. Plus, we need to design our systems for that 7,000 hours and use other components for the left extreme and the right extreme. This allows us now to simply hook up to a water loop, convective circulation loop, thermal highway, whatever you want to call it, run it most of the time, and then pick up these other things like a ground heat exchanger or other things. Next slide, Carrie. So we have lots of different types of thermal storage sources. You've seen and probably are familiar with controls. We can actually move energy from floor to floor for temporary storage. And if we have time, Carrie will tell you a great story about when he did that at one of the large buildings on a university complex, excuse me. Then we have a ground heat exchanger, which is primarily a thermal battery. Okay. Now we can go into other things like ice storage on the right, or phase change materials that can be engineered to change their phase at specific temperatures. And when we start doing this in mass, it really starts working well. Actually, a very large volume of water does the same thing. And now, with the thermal highway, we take advantage of convection, what's being circulated, and conduction, the quantity of fluid that's in that system, and then add to it phase change material. So we can have these additional storage systems and stability for the system with these processes. Next slide, Carrie. And this is my favorite example of a phase change material. Now, I've just got to tell you that Carrie and I do share these, and generally every Friday afternoon, okay, we talk about phase change. And the phase change will be within whatever type of whiskey or bourbon or whatever we're having, with some really nice ice cubes. And here you'll see they've done it perfectly, 2 cubes of ice in some liquid. What is apparent about this is that while that ice is changing phase from a solid to a liquid, we're having constant temperature. And that's why those drinks are so refreshing, because they hold that temperature as that ice is changing phase. Now, it does get diluted to the other liquid you're trying to imbibe, but it still performs that service of holding that temperature constant as it goes through that. And we find that quite advantageous. Next slide, Gary. So we're going to talk about some of these configurations. There's all kinds of words. We're going to try to unify these words. Carrie and I have worked with IAPMO and a number of other deals, trying to get language that we can all use, that we can bring over to ASHRAE, which I'm a member at ASHRAE, a bunch of other stuff. Anyway, we're building language that is going to be common to the industry. And that really needs to happen. But on the left, you see a hairpin loop. All right. It's just a circulating loop that goes out there and got buildings that connect to it. Next slide. Click. One more click. Maybe he's asleep.
No,
Click.
sorry,
What?
Garen, my volume just disappeared.
Okay.
I couldn't
Well,
hear
give me
you.
a click, please.
All right.
We're doing good otherwise, I think. All right. Now you can have a perimeter loop that might go around the block, a community or something like that. And then you have some buildings that outline to it. Next click, there you go. Now here's where it gets really good. Let's combine these, all right? And now we're going to be building a central loop that is primary with, you can call them geomicro districts, secondary configurations of whatever you want. But notice on the one on the right, we have the big hairpin, then we have the smaller loops. And we have a one pipe connection into that gigantic loop that's running by everything. Each building connects to its own internal loop with a one pipe connection. When we do that, that's when we can harvest, store, and reuse wasted energy. That's really critical to understand. Also, it allows us to greatly reduce the pumping that's required on that central hairpin loop and on each micro loop. All we're doing is moving them to share the energy. And we'll pick up those sources and sinks as we go through that. This is something new that people haven't seen a whole lot about. So when we talk about these sinks and sources, buildings add or remove thermal energy. All right, click. Ground loops, same thing. Add or remove thermal energy and store it. Click. Cooling towers only remove thermal energy. Next. Waste heat from power generation, CHP, only add thermal energy to the loop. They do provide KW and KWH, which is a good thing. Next. Now we're going to look at wastewater energy recovery. They allow us to add or remove thermal energy. The built environment, the retrofit for a large community can come through these deals. And with this, I'm going to turn it over to Kerry. He's going to talk about this, but I want you to pay particular attention when he talks about the various microgrids that are in here on the thermal highway. They are all independent and isolated, as is each building on the loop. So go ahead, Kerry.
Okay, I think all of you now have said, okay, that sounds like it's great in theory and everything else, but is it practical? Can we implement it and so forth? Well, we've been doing this since about 2002 at various stages. About 2007, we started on a college campus. By the way, the area that we're showing here is about a half a mile square in downtown Grand Junction, Colorado, and it's Colorado Mesa University. The reason we use this is because it's a 4,000 ton system that has been literally built from scratch and pieced as the college expanded and so forth. We were able to turn on, add additional buildings. So in this particular case, these are the number of buildings and places where we have are connected to a central loop system. The central loop system in this particular case is an 18-inch pipe. It's full of water. There is no antifreeze and stuff, and we have various assets spaced around the system. To do that, make it work, we talk about practical application. We had a general central valving. We have some additional mechanical spaces so that we can independently pump sections of this. There's a main mechanical room here, there's another here, and then there's a third up here at the sports center. And what we've done is we turned it around. We've enabled ourselves to isolate and treat it just like a grid that we are going, whether it be a water grid or electric grid or a natural gas distribution system. So all of the things that come into consideration with the installation of a utility also come into play here. And what we did is we took this in steps. The first step is this group of buildings right here where we've been able to move, that were new buildings that were put together. We started in 2007. We brought them together, total of about 1,000 tons. And as we started to expand the college, we decided, well, we needed something to offset this. We started looking at different uses of the buildings and what they would add. So the next step was to add the dormitory so that we could pick up the domestic hot water, where this is primarily a cooling load. This is going to be primarily a heating load and stuff. The kids are going to be living in here when it's 0 degrees during the winter. By the way, the temperature in ground tension gets from about 0 Fahrenheit all the way up to about 125 Fahrenheit. And so we have a good range and stuff. We are dry. Well, this was the third microgrid we added and stuff, and you can see these are all connected. All these buildings are complementary. This is primarily has a huge Olympic swimming pool, plus the basketball courts and all of the other sports facilities for the university. And then as we start to build and expand to the, this would be to the west, by the way, and stuff, we've got a fourth microgrid in here, which is mixed use, hotel, medical center, classroom buildings, additional dorms, and so forth, so that we can do it. And as we do, and each one of these grids is both isolatable and pumpable by itself. But right now, we're literally sharing energy, all the way from the generating from the center of the campus out to the perimeters and so forth. So we also have a couple of assets. We found a couple of things happen that were magic. We could use other assets. This is an irrigation system for the entire university and stuff. That's a source of heat and cooling. This ball field just now was just yesterday was connected. The irrigation system to this ball field was connected to a secondary source so that we could turn around and get some additional cooling. And there's also a new loop field that was just put in that was commissioned yesterday. So this is a dynamic and growing process. It doesn't have to be static. And in this particular process, we now have 4 cooling towers as of yesterday and stuff. We have a total of about 1,200 tons of cooling capacity right now in cooling towers to shed heat. We've got about 200,000 vertical feet of bore field spaced across the campus and so forth. So we have thermal storage. We have our primary heat rejectors. This system has boilers attached to it, but nothing in this system has had to initiate a boiler fire for the last 13 years, other than some domestic hot water topping that we're doing. And we're going to talk about that a little bit later. But
Barry, what's the low, during that period, what was the low temperature experienced here?
The lowest temperature we ever saw on the loop, the distribution loop, Jared, is that what you're asking?
At weather.
About -10 Fahrenheit.
So we're not talking about a warm climate here. I know some people.
No, this is the Rocky Mountains. This is a mile-high city.
Yeah.
And stuff. We do not have the humidity to deal with you guys have, but we definitely have the heating loads.
And what's the high temperature?
About 125.
Yeah.
Usually about the end of June. So we really do have a range here. And the interesting thing is I have another slide that we do in a special demonstration of this. Our temperature ranges on this ambient loop. Right now, we're balanced in the system. Our lowest temperature in the winter is 60 degrees that we've seen. Typically, it stays 63, 64. The highest temperature in the summer was at 95, and we had to kick in these towers. And it was right at the beginning of school in August when the kids were coming in and we were opening up new buildings. I'll show you another slide later. This one in particular, I think, is the one this is the slide I wanted to talk. And this is a demand plot over 3 years. And what's happened is we've taken the campus in a 3-year period we demonstrate here from 800,000 square feet of conditioned space to 1.2 million on this system. And what you can say that we have plotted with this heat pump system, we've been able to contain the demand of the system in a 1 megawatt range. Well, we've been looking at CHP in the system because power in Colorado, and particularly power at peak, is extremely expensive and stuff. So we want to turn around and start to figure out how we can corral these numbers. By the way, these outliers are usually August or September when the kids are coming back to school. All the doors are opening and closing. We're cranking up systems. And you can see as we start to add square footage, stuff, we get a couple of extra hours, outliers, more kids. But the campus started out at this point was about 4,000 students. At this point, we're at 11,000 students. So in that 3-year period, that's the growth we've seen. And you can see we've got these layers that are walking out. But we now have determined that a system of about a half a megawatt would augment and bring our temperature up maybe 2 degrees in the winter, which was wonderful. Because we increase capacity and efficiency of our heat pumps and stuff, but we would eliminate all of these outliers. So as we go through, so that's kind of a real interesting way. You talk about decarbonization. We are a coal-fired economy out here for the most part. We do have natural gas plants, but in Colorado in particular has a lot of coal-fired plants. So what are we going to do for distribution? How are we going to turn around and take this? What new equipment? What's enabled us to look at these things differently? Well, one of the things that we're starting to look at is what we call 6-pipe systems. This is a simultaneous heating and cooling system that we can turn around, and when we do full load or mixed load, when we're simultaneously heating and cooling, we can see EERs in the neighborhood of 27 in the cooling side. Simultaneously, we can see COPs up to 8. And we're looking at about 0.4 kW per ton on this system. Now, this is a heat pump system. If it's under 410A and stuff, it's probably got a top range of about 120 degrees Fahrenheit and stuff, maybe 130 if we want to push it. But we can also chill and make ice, do a hockey rink on the cold side. It's a matter of what we do. And the way these 6-pipe systems work is there's a supply and return for the chill water side, a supply and return for the hot water side. And then when one loop or the other is imbalanced, the load and the two are imbalanced, it has 2 more pipes that lets you go to a central loop or to some sort of a storage system or even conventional equipment, but you can add or subtract energy. So conventional system would be boiler cooling tower, ground source system might be the ground, might be the thermal energy storage, and so forth. So you can look at that. So we're turning around and constantly moving and recovering the wasted energy. And the reason for these efficiencies on the box have to do with how the system is handled. Just another picture, just to give you a little bit more complex and stuff. These are modular. This all lends itself to retrofit because this will go through a 36-inch door. And we can start to look at. So if you think about these modular chillers that we're looking at, could we now retrofit buildings either in toto or floor to floor or zone to zone by simply setting these things up to move around and temporary while we don't disturb the rest of the occupants in the building. This is a 6-pipe system with a CO2 heat pump generator, a new innovation that we're turning around and starting to be able to apply in the U.S. 5 years ago, this wasn't available and it wasn't even UL listed in the state. But here in this particular case, where we're looking at a new refrigerant and a different methodology, in this particular case, we're looking at retrofitting a 180F, what would typically be steam or high temperature hot water distribution. And we can start to look at system COPs. And we can start to see what's happening here with these generators and stuff. But you can see our output temperature in the heating side is about 176 degrees. And in this particular example, at the same time, we're making cooling at about 41 Fahrenheit. So this enables you, of course, this is the chiller range. This is the range we use. This is nothing uncommon. But you notice that we have an ambient loop here that we're either drawing or sinking energy to help maintain this at its highest curve, this heat pump. So this is this is one of the first applications that we can start to look at about a practical way to heat and cool a high temperature system. And again, it's going to depend on your distribution system. Another piece of equipment, what I wanted to show you just the way one of these skid mounted CO2 heat pumps looks like. What I want to bring to your attention is when we're getting into these high temperatures, look at the COPs we're able to maintain. Heretofore, this is unheard of. Now, the CO2 doesn't cool as well in the sense that its COPs are a little bit lower on that side, but this is a primary source. So if you've got a heating dominant system, this might be one of the things you want to look at. And by the way, these are being now built modularly. This one is kind of built to order. And we've seen stuff up to about 2,000 tons. So this is another one. We talk about some of the things, the different systems we have, condensate return and stuff, and what happens to it. Does it go back to the plant and recaptured and reused, or is it wasted? Are there other opportunities? This in particular is a organic Riken cycle CHP unit or generator unit. So we can now take with these micro turbines and so forth, water as low as 160 degrees and stuff, and generate electricity, a secondary term or secondary use of that waste energy that we're talking about. So we may be able to turn around. And when you start to use these systems like this, the electricity generated starts to offset the other assets that we have and the cost of the other assets. So it's kind of a double whammy, but it's now capable. Again, 2 years, we didn't have anything listed in the United States to do this. So what I wanted to bring out to here is the different refrigerants. As we change refrigerants, we can tailor the range of the output of the machine. So we're looking at a range right now, in this particular case, output of what we were just showing you of 158 Fahrenheit to about 248 Fahrenheit. That is huge. That's your heat source. Your cold source can be between 32 and 140. The working fluid here in this particular case, the refrigerant, is 1233 ZD. These are all esoteric refrigerants that we can tailor, that are all components that we can look and get to today. I wanted to show this an alternate refrigerant, hydronic heat pumps, and this is actually a system that changes the refrigerant based on the application. And here are the different refrigerants we can turn around and look at. We've got, for lower temperature, would be 134A. As we start to move up, some of these temperatures expand the maximum temperature that we can use on the system. So again, if all we're doing is taking care of Legionella, we need to heat to 145 to 160. We might use one refrigerant, and that will give us a curve that will show efficiency that we can pick up and how we can recover that. We use another refrigerant, we could bump it with a smaller unit. This is typically, and has been done, all the way up to 185 degrees with 134A, which is a very common refrigerant in the United States. So as we're looking for, and these are just different applications, and as you can see, we're looking at centigrade here and stuff. I want to point it out. So we got overboiling in some applications and at this point. So technically we have a steam replacement. So, and changeover, high temperature. Jared, we still, it's been pretty quiet. No questions or anything?
There was a question that came in from Ed. I sort of answered it in the Q&A box, but what's the distance range that thermal energy networks can cover? And I said, my response was it could be many miles of connected networks, right? Like we're not talking about one loop, we're talking about a lot of loops that are interconnected, and that it wouldn't be unlike the current natural gas network or even the sanitary and potable water pipe system that is like a spider octopus all over the place.
All right, thank you.
Yeah, I don't know if do you have anything to add to that response?
No, I think you did an excellent job of that and go through. I'm watching my watch and making sure we have get some of that stuff in.
Yeah,
there
we do want to get more questions in, so let's try to roll through this.
Jared, Garen. One thing to think about is water loops, probably not as far as CO2 loops. You're going to see CO2 loops start coming in the future, which means now your natural gas industry has a natural movement in with their distribution lines. Not through the supply lines, but
yeah. I mean, that's a whole discussion, because you get into lower pipe diameters for heat transfer, and then you also we could potentially get around the regulatory issues that currently exist that ban gas utilities from transporting anything but gas. And so CO2 as a refrigerant is a gas. And then even more mind-blowing is, can we get into CO2 capture, utilization, and sequestration using a refrigerant-based system that also transports CO2 as waste? So
yes, and there are systems like that in operation today. I just wanted to bring that up. Thank you. Go ahead.
Very, very interesting opportunity. So, okay, just this is for here's just some ideas about how we do this. This is not the only way to do it, but it's kind of a progressive, a checklist of different ways we can do. So what I want to do when I turn on and I take a building, and we're looking for the Empire Building Challenge, and we're trying to retrofit and decide what we can do with it. The first thing I want to do is I want to turn around and see what's making that temperature I have to deliver, that 180-degree temperature, if you're talking about hot water distribution. Why did I have to do that? What particular area did I have to deal with? Was it, or just was it was convenient, it was there, so we'll tell her the whole building to it. But in case of driver buildings and driver zones, for example, a gymnasium might be a driver for both outside air and air conditioning for a rec center, for example, and stuff. And it in turn, because it needs maybe 41-degree chilled water to get to it, to air condition it adequately. But the other buildings or other zones in that building would only require 50-degree water. What could we do? Well, maybe by identifying it as driver zone, and it lets us turn and isolate that and maybe put a different piece of equipment there. Or a different way that we distribute, so that we can turn around and get more energy out of it. We might want to twin coils. There are all kinds of different ways we can look at that, but we want to identify those driver zones, because remember, we're looking at part load. We're looking at taking the peak driver loads, possibly with conventional equipment or possibly with a piece of specialty equipment. But in either case, we don't need to treat the whole building. As we move towards ambient temperature distribution, particularly with a heat pump, meaning 50 degrees to say 85 degrees on the source and of the source fluid and stuff, the more we move towards that middle range down to about 70, the higher the efficiency of the heat pump. When we increase the efficiency of the heat pump, we also increase its output or its capacity. And in cases when we increase the efficiency, we're increasing the COP and we're increasing the system COP. So we want to look at identify areas for cogen and or heat recovery, wastewater. Think of that. What might we need to do? Identify wasted energy recovery opportunities and part load opportunities and stuff. This is where the equipment gets smaller and we can go to an ambient temperature faster. Identify alternate heat sources. Very important, because we have to replace in the building. If we were supplying steam to the building, we have to turn around and supply an alternate source of energy if we're going to turn around and mitigate the amount of use or mitigate the steam use. So we want to reduce the delivery temperature in the shoulder months, the hydronic. Remember our bin data graph, that's 7,000 hours. We want to tailor this to that. We want to turn around and have the pumps running at the lowest speed. We want a variable speed compressors in some of our distribution system on the heat pumps, so that we can wind that down or turn down, and the affinity laws become our friend. So supplement the problem areas to further drive delivery temperatures towards optimal, high or low. Stuff, we talked about that. Investigate twinning or replacing coils in the delivery system. Stuff, what can we use the existing equipment and modify how we distribute the energy to that coil or to that device. Investigate alternate heat pump refrigerants and heat recovery options for equipment replacement. Drive system to heat pumps and economizers. Get that entering water temperature down, move it to ambient, so that we can turn around and we can convect and conduct that energy to the systems, and then utilize an effective and efficient tool to lift or depress the zone energy or zone temperature. And then, as I said, we want to design and take that loop. So, quick example. So other heat sources, those are some of the things we need to look at. Wastewater, black water, solar thermal, steam condensate. This is where it really applies, maybe in the high temperature mitigation. As we move to plug and play, we want to look at other buildings as being sources and sinks. geothermal, capture, storage, time of use. What does it do to our demand profile? What does our do consumption? Standing column wells, in foundation drilling, we have those capabilities, been doing it in Vancouver for almost 20 years now. Surface water, we can look at ambient. We have plenty of that in New York. Subsurface city tunnel or air recovery. This is huge. And so there's a huge amount of energy. And what I've seen articles that indicate that the majority of the heat in there is fundamentally brake energy for the subways. That's where that's coming from. And then again, wastewater, black water. So think about these things. What you use. And the neat thing about heat pumps is the small temperature delta here can give us huge amounts of energy available to us and stuff. And so we're starting to capture those incremental pieces as we go through. But we always focus the system to pick up the largest, or if you will, the low-hanging fruit, because they're going to get our biggest decarbonization right there, and it's going to be immediate as you move through that. So here's a system. This is kind of a neat one that we go. This one doesn't have a ground source and stuff. It's a system that's being retrofitted in one of our major cities and stuff, and we're using the heat from a CHP unit. And this is our energy center, and it has CHP, and it has conventional equipment attached to it. By the way, a couple of boilers to augment it if we need to. The delivery here is 180 degrees, typically. So, and you can see we kind of have some different systems. This is a simultaneous system where you can simultaneously heat and cool. Could be just about anything you want to talk about. VAV reheat, doesn't matter. Stuff. This is a dual deck distribution, a unique animal all in itself and stuff. But what we're going to talk about is what a lot of these systems in the older buildings are actually 2-pipe switchovers. You're either heating or you're cooling. This is a target. It's a big target. And it's an easy target to turn around and look at it. And we're going to talk about a little bit about how we do that. You might notice some real interesting little plumbing issues here and stuff. What these are valving and set up as we modify the building and what's going into the system, so that what happens is we're able to turn on a heat or cool, and we can change over from a parallel system in the high temperature distribution mode to, as the temperature walks down, a primary secondary system in the low temperature or ambient range, so that we can utilize more heat pumps in these buildings to offset some of this. So we built the system. We have a couple of things that we did. We replicated some of the switchover system. We're saying we need to do this. What this little modification did was turn around and take my energy system and decouple it from the main system when I move to ambient. So this now becomes effectively a large boiler injection loop if I need extra heat or if I want to utilize it. And by the way, the CHP generated here tends to offset all of the cooling costs in this particular situation. And it's about 1/4 of the total electric load. So we were able to look at 1/4 of the electric load. We were able to mitigate approximately 50% of the high temperature load and all of the cooling load because of the electric generated. We also take a look at this, what we have in our distribution. This is our 2-pipe plumbing, but we also need to start to figure out what we're going to do here. How do we take this from 180 degree distribution down to something much lower than that? Well, maybe what we need is a little bit more cooling space. In this particular case, this building has heating and cooling in large air handlers, where we can come back and we can start to talk about twinning these coils. So what happens is, and we may change the prime movers while we're at it in here, but as we go through. But what I wanted to do is, here's one of the outcomes as we move this. So in the summer mode, what we're going to do is we're going to keep those systems independently by closing these 2 valves. We'll use the chiller, the cooling tower. And if we need simultaneous heating, we're going to be using our energy center or waste heat from the CHP to turn around and drive it. And that particular time, we will drive almost 100% of the heating load with the CHP. So, and then in the winter mode, we might want to turn around and we have a crossover system set up so that we can now turn around and use this second cooling temperature, and we can start to reduce the distributed temperature to those zones. That can be done with some valving retrofits in the building. The common being is that we picked up this extra capacity, therefore we're able to lower the temperature. We're able to move to ambient. So that said, we got it all in, but